I want to introduce topos as well. So what is topos theory? I'm still a 15-year-old.
Very good, yeah. Okay, so for the experts out there, I preface this by saying that what I'm describing now is Grothendieck toposes, as opposed to elementary toposes. But everybody else should forget this remark. So here's the golden way, I think, to enter topos, the notion of toposes, at least for the kind of purpose that we're after here. So we've seen before that this key aspect of category theory is that it identifies every object it identifies the internal structure of every object by the relation that it has to all the other objects in the category. There's actually, I mentioned it very briefly before, there's this thing called the Yoneda lemma, which makes precise this idea that to understand the object X is actually the same as understanding the system of all the maps from all other objects into it. So we probe it with all other. Okay, so that's beautiful conceptually, but of course it's practically a bit useless sometimes, because if your category is large, you have little chance to get a hands-on understanding of what all these maps are, like, because there are many topological spaces, right, to say the least. And so you might say, well, understanding my topological space X directly is not going to be harder than understanding the maps from all other topological spaces here, because, And so the idea of topos theory is to say, well, okay, let's look at sort of more well-behaved spaces that are probed, whose inner structure is detectable by mapping a small set of probes into it, not all other things. Well, the statement will still be true. If we map everything into them, we can see everything. But maybe there's a smaller set of probes, as we're going to call them, of maybe well-behaved little objects that we know about. And we say, well, it should be sufficient to know how all these probe objects map into my given space or object. That should be sufficient for knowing its structure. So toposes will be categories of spaces with that property, that there is some set, or actually a small category of probe spaces by which they can be fully probed and determined. So let's make it a bit more precise, okay? So first we want to say the set of probes should itself be, as everything we're going to be talking about, should itself be a category. So we want to know what counts as a map between our probes. And this will specify the kind of geometry we're talking about. So you should start thinking now about these probes as being, for our purposes at least, as being little model geometries or little abstract charts, and the map between them as being the maps that preserve a given notion of geometry. So, for instance, a good example to keep in mind of a category of probes is the category of what I like to call Cartesian spaces. So of manifolds of the form R to the n, like the point, the line, the plane, the 3D Euclidean space. That is a small category. It's really just a set of things. It has one object per natural number. And now we can regard these Cartesian spaces in different notions of geometry. For instance, we can declare that the maps between them, we allow all continuous maps. That means to regard the Cartesian spaces as being topological spaces. And we would be saying the Rn's are like a basic building blocks of topology, of topological space. But we could also say, since there's also smooth structure, of course, on Rn's, we could consider the category of Cartesian spaces with smooth maps between them. And we say, we take this as our probe geometry, and that will make the resulting generalized spaces that we're in the process of describing, will make them behave like generalized smooth spaces, as opposed to just generalized topological spaces. So they have a notion of not just continuity, but of differential geometry, of smoothness. So these are the examples to keep in mind. Or you can take Rn's of even dimensions, so Cn's, and take the maps to be holomorphic maps that respect the complex structure. Then we're talking about a notion of complex geometry. So you see the pattern is the kind of geometry you want to describe, you find the most elementary building blocks of it and elementary maps between them. And now topos theory is the answer to the question, what is the most usefully generalized notion of space for that geometry? So what is the most generalized notion of smooth space? If we start with differential geometry. And that's going to be, that gets us into this realm of physics, because this gets into this question, like what are the, for instance, spaces of fields in actual physical theory, because they're huge, not even infinite dimensional anymore spaces, of which actually the textbooks are silent about where do they actually live. So we want to, or one application of this topos theory to physics will be that we can build a notion of very general smooth spaces, such that, for instance, spaces of field configurations are still examples of these. Okay, so but let's continue to describe what is a topos. So I said it's so we have this category now. I'm going to call it S for side. This category of these little probe spaces, and now we want to say, okay, let's envision. So we're bootstrapping a notion of generalized spaces into existence now, as follows. We say, okay, let there be a generalized space X. We don't know yet what X is, but we want to say it should be probable by our probes. Yeah. So we want to say that for each probe, there should be a set of would-be maps from the probe into it, even though there's not yet a notion of maps, because we haven't even said what the space is. But let's just envision, bootstrapping it into existence, that such a set exists. So we declare such a set. And then we say, well, for minimum consistency, so our probe space will be U, the target space will be X. It doesn't exist yet, so think of it as X in quotation marks. But if I had a map from U to X, then clearly if I had a map from U prime to U, which I actually know, it's a map, like a smooth map, for instance, of my RNs, then clearly the composite should qualify
from
as
U prime to X.
From U prime to X. So I want to demand that these composites exist and that they behave properly. So that I keep composing, I keep forming these composites in a compatible associative way. What this says, if one thinks about it, is that the collections of sets of probes is a functor from the opposite. It's a contrariant functor from this category of probes to sets. It sends probes to sets and sends maps of probes to the corresponding pullback operation on these sets. So the technical term for so it's contravariant for, let's forget this for a moment. So the technical term for a set-valued functor is a presheave. It's just a term that people would say. It means nothing more at this point. It comes from ancient days when people, I think this comes from, sheaf, these are agricultural terms. This comes from the days when the mathematician who would look up and look for how to name his object. So he would look out of the window and what he would see would be agricultural land. So, and he would see the sheaves sitting there. And he called it a sheaf. That's, okay. I think, what this terminology comes about. It's really sets of plots. That's a good way of thinking about it. All right. So that kind of, we're progressing to the point that we want to say, well, we already said that an abstract or generalized space modeled on probes, on given probes, should be this functor, assigning to probes sets of plots. There should be a little bit more, namely, there should be a notion of gluing. Like my category of probes should have a notion of what it means, or will have in practice, of what it means to build a bigger probe from smaller probes. So you can see it with the example of the Cartesian spaces, maybe. Think of R2. You can take the plane and you cover it with lots of open balls, or just cover it with two half planes. So you take the left half overlapping a bit to the right and the right half overlapping. Both of these halves look again like R2s. Now, if you have a map into your would-be space from the left half and another map from the right half into the space, such that on this little strip where they overlap, they coincide, well, then clearly you want to be able to conclude that you actually build a map from the total plane. This means to glue these maps. And, this is a little technical thing. This is not, if we just have this presheaf, this need not hold this gluing property, so we impose this gluing property. This is called the sheaf property. So we declare that, well, first of all, we need a notion of how to glue probes. This is called a coverage, so how to cover one probe by other probes. But once we have that, we say of all these assignments of plots, we want to require not just that they're functorial, but also that they glue in this sense. Now we're there. This is called the sheaf condition. So a set-valued functor on probes that satisfy this sheaf condition is called a sheaf. And since our generalized spaces are now incarnated as these functors, sometimes called the functors of points, that was Grothendieck's original topology. They kind of check what is the internal structure of, like in particular, the points of our would-be space. Since these are functors, they automatically live in a functor category. So we've already built a category now of generalized spaces, of which the generalized space is incarnated as its system of plots, and a homomorphism of generalized spaces is a natural transformation between these. So, okay, one has to maybe sit down and take a piece of paper and work out what this means, but this is a very nice construction, actually. And now that is a topos. So a topos is a category that looks like, meaning it's equivalent to, in the technical sense, it looks like such a category of generalized spaces.